Good afternoon, participants. To those who are in India, because we find Dr. T.K. Bandyopadhyay, he has also joined from US. So it's a night for him. So midnight for him. So midnight for Dr. Bandyopadhyay and afternoon for those who are from India. This is a lecture series again, the third one in the row, and part two for the lecture which we had earlier. It is on IS 1893 Part 1, 2016. The title of this code, though, is Criteria for Earthquake-Resistant Design of Structures. Part 1 is for General Provisions and Buildings. We have with us, it's a continuation of the earlier lecture, Dr. Ashok Kumar Jain. Though we have known him since the last lecture, still a little bit of his CV. Dr. Jain obtained his BSc from Meerut University in 1968, B Civil with honors from University of Roorkee in 1972, ME Structures with honors from University of Roorkee in 1974, and PhD from University of Michigan, Ann Arbor, USA in 1978. He is a recipient of several gold, silver, and bronze medals from the University of Roorkee. He joined University of Roorkee in September 1979 as lecturer and became the professor of civil engineering in 1991. Later served as head of the department. He was director MNIT Jaipur from 2003 to 2005. He retired from IIT Roorkee in May 2016. His main areas of interest includes multi-storied buildings, towers and bridges, earthquake-resistant design of RC and steel structures. He has authored 5 textbooks, details we are not going just now, and has published over 145 papers in reputed national and international journals and conferences. He carried out pioneering work on the post-buckling inelastic response of steel bracing members and concentric braced steel frames. He is a fellow of the Institute of Engineers and Indian Association of Structural Engineering and life member of Indian Concrete Institute, Chennai, Indian Society of Earthquake Technology, Roorkee. Dr. Jain is also a consultant in many agencies in the area of structural engineering and earthquake-resistant design. So with this, I would now request Dr. Jain to go directly to the lecture. We anticipate there will be many questions coming up after the completion of the lecture. So now over to Dr. Jain. Yes, sir, please.
Thank you, Mr. Ghosh, for those nice words. As you have already mentioned, this is the third lecture in the series. Basically, the idea was to tell you what are the various issues related to the use of IS 1893 Part 1, 2016 code. So the first lecture was regarding the nonlinear behavior, that is the inelastic response of steel buildings and response direction factor, how to generate the response direction factor, the plastic hinge mechanisms, the meaning of ductility, and how do we design a ductile structure and how it is supposed to behave during a severe earthquake. Okay. Second lecture, which was held last week, that was regarding the mode shapes, the first mode, the fundamental mode of vibrations, and the multi-degree freedom system, and how to apply the earthquake force, how to compute earthquake force, and how to apply the static method of analysis and the dynamic method of analysis. So I thought that those lectures, the previous 2 lectures, were essential to understand the various provisions of 1893 2016 code. Earlier, this code was quite easy, and therefore there was no need for you to understand the fundamentals of structural dynamics. But day by day, the code is becoming more comprehensive, more complicated, and more technical in nature. Therefore, those people who have a background of only undergraduate courses they are having a lot of difficulty in understanding the various provisions of this new code. Okay, so that was the reason why I thought that some aspects of dynamics should be covered before we start talking about the various provisions of 0893 code. So my topic of today's lecture is understanding IS 0893 Part 1 2016 code. There are two amendments, A1 and A2. So please make sure that you have access to these two amendments. Otherwise, you can download all these codes as well as the amendments from the website of BIS, which is all free now. So these are the keywords that I will be covering. Now, understanding Indian codes on earthquake. It is quite difficult to understand 1893, 13920 and 16700 codes, mainly because of the following factors. The level of seismicity in India has been raised equal to or more than that in California and Japan without any quantitative or even qualitative evidence through various stipulations. These codes have been developed using copy, paste, and edit technology. There is no correlation between the original clause and the final clause that has appeared in our code. The BIS did not produce any commentary nor any background information is available in the minutes of the meetings which were held to revise this code. So in the absence of all those information, it becomes really difficult to understand and explain the basis of various clauses of IS 1893 code. Some of the popular commercial software for the seismic analysis are unable to comply with some of the clauses of IS 1893 code because of lack of any logic. Please remember, as I mentioned in my previous lecture also, that although those software claim that they are following the 1893 code 2016 edition, but if you go through the manual, user's manual, you will find that there are certain clauses which they are not able to comply with. And they are clearly mentioned in their user's manual. So please go through the user's manual and find out which clauses are not being implemented. Writing a code is an art. I've been associated with this activity since I began my career in 1974 at the Department of Earthquake Engineering, University of Roorkee. 1975 edition of the code 1893 was at the time under preparation. Since 1982, I was associated with the revision of IS 800, later on with the revision of 456, 1343, 3370, 4326, and so on. There was complete transparency with regard to the source of the specification, why a clause need to be modified or not modified, and so on. Each revision in each code bore the stamp of the chairman of the code committee. Each point of view was given due respect and consideration. They were men of eminence with vast practical experience. The bottom line in writing a code is the code must be user-friendly and it is meant for a common designer, not for an expert. It need not reflect the latest research, but must reflect the latest best practice. There should not be any serious mismatch between the existing buildings and the new ones to avoid any need of retrofitting of newly built buildings. Innovation in design must be encouraged. The code must be flexible and forward-looking. The first draft of this code came out sometimes in 2006. The last draft came out in February 2016. Comments were circulated. The committee approved the draft in June 2016. The final code is, incidentally, nowhere close to any of the drafts ever widely circulated for this 2016 edition. There are many changes throughout the code having far richer consequences than those were circulated in June or approved in June. As I mentioned, please do refer amendments A1 and A2 of this code. Now, significant changes. What are significant changes in this code? A very, very brief forward. The previous editions gave a detailed explanation and background of the earthquake resistant philosophy adopted in the code. The forward in 2002 edition ran in 4 A4 size pages. The forward in the draft 2016 page code ran in 6 pages, but the forward in the final code runs only in 2 pages, first and last page. I wish the forward was much more detailed, giving the philosophy and background information for the benefit of the users. Many definitions have been drastically changed and deleted, such as maximum considered earthquake, MCE, design basis earthquake, DBE. These definitions have not been deleted. Soft story and weak story, earlier they were quantitative, now they are simply qualitative. Minimum lateral force is specified in all seismic zones. Why? What is the problem if wind governs the design? Now, once they have deleted the definitions of MCE and DBE, it becomes very difficult to explain the presence of factor 2 and R in the base shear equation. Treatment of soft story and weak story with URM, unreinforced masonry walls is specified. Treatment of RC frame buildings with open stories and URM is specified. Treatment of torsion is changed, made it more difficult to implement even with the help of 2 widely used programs, STAT and ETAPS. 2 different response spectra introduced, different for static and dynamic analysis. White Amendment A2 2020, clause 6.3.3.1 has been made explicitly applicable to buildings in seismic zones 4 and 5. It means that each and every RC building needs to be designed for vertical component of the earthquake, which in my opinion is completely unnecessary and not required. It's simply crazy. Seismic design philosophy, although deleted from the preface in 2016 edition, it remains the most universal design philosophy in all countries of the world till date. Minor earthquakes, there should be no structural damage. Moderate earthquake, there can be minor structural damage, and severe earthquakes, major damage, but without any collapse of the building. And these different mechanisms, partial collapse, full collapse, and the story mechanisms, etc., have already been discussed in my first lecture, which was held in the month of June. Now, in 2002 edition, it was stated that the design lateral force specified in the standard shall be considered in each of the 2 orthogonal horizontal directions of the structure. For structures which have lateral force resisting elements in the 2 orthogonal directions only, the design lateral force shall be considered along one direction at a time and not in both directions simultaneously. Structures having lateral force resisting elements, for example, frames and shear walls, in directions other than the 2 orthogonal directions, they shall be analyzed considering the load combination specified in 6.3.2. This clause has been deleted in the 2016 edition. Now, coming to the regular and irregular configurations. A perfectly symmetrical building. How do you define a perfectly symmetrical building? It should have symmetry with respect to geometry, mass, stiffness in plan and elevation both. Okay, so if you have a structure which is geometrically symmetric in plan and elevation, mass in plan and elevation, stiffness in plan and elevation, that would be called as a perfectly symmetrical building. And in that case, tables 5 and 6 are simply not applicable to such buildings. But table 6, clause 7 is a culprit. It will have equal translational periods of vibration in the 2 orthogonal directions, or it may also result in a diagonal mode of vibration. Many designers interpret it as undesirable mode. That is an irregularity. Okay, because structure is perfectly symmetrical in plan or in elevation, they intentionally make it unsymmetric building so that the first 2 translational mode periods are away from each other by more than 10%. Remember, because it is a perfectly symmetrical building, a square building in plan and elevation, therefore, the first 2 modes will be equal. But that clause says, as I mentioned, the clause table 6, clause 7, that the first 2 translational periods must be more than 10% away. Therefore, the designers are now forced to make a perfectly symmetrical building as unsymmetric to satisfy this clause. they forget that about the advantage of zero structural eccentricity and nil torsion in a perfectly symmetrical building. Okay, this clause of 10% away is simply not applicable in this case. So there is a collateral damage, is not a perfect example of the collapse damage caused by this seismicity activism. Both clause ASC 7 and EC Eurocode 8, part 1, specifically state that a similar regular and irregular configurations. I was talking about the perfectly symmetrical building. A perfectly symmetrical building means symmetry with respect to geometry, mass, stiffness, or in plan as well as in elevation. Therefore, in such a case, table 5 and 6 are simply not applicable to such buildings. Okay, but table 6 clause 7 is the culprit. If you take a perfectly symmetrical building, that is a building which is perfectly square in plan, it will have equal translation periods of vibration in the two orthogonal directions, or it may also result in a diagonal mode of vibration. Many designers interpret it as a undesirable mode, that is, it is an irregularity. They intentionally make it unsymmetric building so that the first two translational periods are away by more than 10%. So they have take a perfectly symmetrical building and make it unsymmetric, make it irregular because of that clause. They forget that what is the advantage of zero structural eccentricity and nil torsion in a perfectly symmetrical building. Okay, it is a collateral damage because of this seismicity activism by some people in the IS Code Committee. Both AC 7 2019 and Eurocode 8 specifically state that a symmetrical building is highly desirable. Clause 7 on buildings in Indian Code omits symmetry as a desirable attribute. Table 5 and 6, these two happen to be the most confusing and difficult for common designers. The original sources AC7 and Eurocode 8 are very well written and easy to understand and therefore implement. Until 2002 edition, this provision was easily understood, but not in the latest edition anymore. As I mentioned, in this clause, in this table 6, clause 7, they have introduced a term called irregular modes of oscillation, vertical irregularity. Okay, I don't understand since when the modes have become irregular. Okay, vertical, they're talking about the vertical irregular building, but they're talking about these irregular modes in plan. I have no idea what they're talking about. I doubt even if they have any idea what they try to say in here. In table 6.7, the buildings in seismic zone 2 and 3 shall ensure that first three modes contribute at least 65% mass participation in each principal direction. And for those in seismic zones 4 and 5, to mention that in addition to the first three modes contribute at least 65% mass participation in each principal direction, fundamental natural period in two directions shall be away from each other by 10%. This clause is unique to India. There is no such stipulation even in AC 7 or Eurocode 8 from where most of the code has been copied. Okay, this is very important for you to understand. This clause is not there. Now, what happens if this clause is not satisfied? How to satisfy this clause? If you have designed your building or you are carrying out a dynamic analysis and you find that this table 6 clause 7 is not being satisfied, then the question arises how to satisfy it. For that, you have to change the architectural plan. Okay, the location of the shear walls, the location of the structural system, or the salient features of this system, columns and beams sizes may be modified, and other things. So you will have to make drastic changes in your basic building so that this clause is satisfied. Irregular modes of oscillation in plan. What is the essence of irregularity? Actually, what is the intention of the code behind this clause of regularity and irregularity? The intentions are very simple and which are reasonable, and they are there in almost all international codes. Avoid sudden change in mass, stiffness, and geometry. See, nobody wants a perfectly symmetrical building just like a matchbox. No, we don't want a matchbox. The intention is to give fairly reasonable
freedom to the architect so that he can come up with his own, uh, you know, uh, building. Whatever he wants to show in the building, whatever changes he wants to make, he should be able to do it. But the condition is there should not be any sudden change in the geometry of the building, whether plan or elevation, sudden change in the mass or stiffness. Okay, you can make gradual changes. You can make the change the building gradually and unsymmetric in terms of geometry along the height of the building. Or gradually you can change the mass. Gradually you can change the stiffness also. But those changes have to be gradual, not sudden. That is the key word. Then another thing is you must avoid torsion in the first two fundamental modes. The torsion is very, very dangerous. I will tell you later on what are the implications of torsion. So please avoid torsion in the first two fundamental modes. And you may have to modify the architectural layout in order to achieve it. Building with soft story. See, in the ground floor for parking, we need open space. Okay, so what most people do, they raise the building or multi-story building on columns alone. On the ground floor, you only have columns, and then on the upper floors, you have infill walls or RC wall and so on. Now, this is a perfect example of soft and weak story, and this is highly undesirable. So this will lead to sway mechanism, and this is what I have discussed in the last term, that this must be avoided. Otherwise, the building is in serious condition with respect to failure. Okay, so this has to be avoided. Now, in 2016 edition, that's how the soft story has been defined. It is one in which the lateral stiffness is less than that in the story above. Now, it doesn't only say the lateral stiffness is less than that in the story above. Now, what does it mean? How much less? 1%, 0.5%, 20%, 30%, or how much? The story lateral stiffness is the total stiffness of all centric force resisting elements resisting lateral earthquake shaking effects in the considered direction. That is the definition given. Similarly, for weak story, it is one in which the story lateral strength is less than that in the story above. Again, how much less? 0.5%, 1%, 10%, 20%, how much? Just because it is less doesn't mean that it becomes weak story. The story lateral strength is the total strength of all seismic force resisting elements sharing the lateral story shear in the considered direction. This definition is simply crazy. In the 2002 edition, let's see how the soft story was defined. It is one in which the lateral stiffness is less than 70% of that in the story above, or less than 80% of the average lateral stiffness of the three stories above. Now, this is a quantitative definition. It can be understood. It makes sense. It was there earlier. But I don't know what was the idea behind the changes in the 2016 edition. Those people removed this quantitative definition and made it qualitative, which makes absolutely no sense. Similarly, weak story. It is one in which the story lateral strength is less than 80% of that in the story above. The story lateral strength is the total strength of all seismic force resisting elements sharing the story shear in the considered direction. These definitions were adopted from UBC 97 ASC 7. They were much more specific, logical, and tactical. Okay, but in 2016 edition, they chose to delete it and replace with the term less, which is absurd. Soft story, table 6, uh, clause 1. The structural plant density shall be estimated when unreinforced masonry and fills are used. When SPD of masonry exceeds 20%, the factor URM in fill shall be considered by explicit modeling and same in the structural analysis. Now, the funny part is the design forces for RC numbers shall be larger of that obtained from analysis of bare frame 2D modeling or 3D modeling, we don't know. So they say that you should carry out a bare frame modeling, that's design one and design it. Okay, and then you model it as frames with URM fills using 3D modeling and again design it. And then choose the worst of these two. Now, how can you have two different independent designs, two independent models with this kind of requirement and design them. Now, how do you compare those, and how do you make changes so that the design is the combination of the worst of the design one and design two? I don't think that people who have written that clause have ever designed even a single story building. That's why they come up with such crazy ideas. The new clause 7.9.1.1 says the same thing. Soft and weak stories. In a simple language, such irregularity is simply not permitted. If you wish to provide a space for parking, then you must provide sufficient RC walls, braces, whether RC brace or steel brace, at appropriate location in both directions, so as to permit the desired movement of vehicles. At the same time, no such irregularity remains in the building. Okay? Floating columns, Amendment A2, dated 2020. Why this amendment? Such columns are likely to cause concentrated damage in the structure and are undesirable. A building with floating columns shall not be permitted if the floating columns are part of or supporting the primary lateral load resisting system. In figures 4A and 4E, the middle figure showing floating columns in tall buildings have now been deleted. Okay, it means now onwards, large column-free lobby cannot be provided in hotels and conference halls with multi-story buildings. That is the implication of this floating column. Floating or gravity columns. Such a column is not permitted to be a part of the lateral load resisting system. It can participate only in carrying the gravity load. It means no bending moment can develop within the column. Okay, now this has caused a lot of confusion, and every designer, most designers have come up with their own innovative interpretations and how to implement this in the software and in their design. Okay, some designers set its moment inertia to nearly zero so that it won't carry any bending moment. Such an idealization is incorrect because you can set moment inertia zero in your model, but how do you make it zero in real practice in a real life building? There, real moment inertia is not zero, so that modeling is not correct. The correct modeling is to introduce movement releases at the ends of each of such columns through each story, but same has to reflect in the detailing of reinforcement. If you can't detail it accordingly, then again, this modeling is incorrect. Okay? Fundamental time period. I've already discussed this clause last week's lecture. So I will not spend too much time on this. In the clause 7.6.2, our forefathers tried to develop simplified equations such as t is equal to 0.1 n, where n is the number of stories, and t is equal to ct h power 7.75, the ct has been defined for different types of buildings. Okay, as I mentioned, the testing of this multiple buildings was done in 60s and 70s in America. These were steel from moment steel frames, and they filled a curve fitting and developed the formula T is equal to 0.028 h to the power 0.8. This is FPS units. They have an upper bound, they have a lower bound. In red color, I am showing here the lower bound. Now, this is in FPS, this formula which I have shown here, and MKS units you already have with you in the code. So T is based on curve fitting of data obtained from measured response of California buildings and other states after small earthquakes. As you will see later, the smaller the period, the larger the earthquake force that was designed for. Hence, a lower bound empirical relationship is used. However, this lower bound period is about 1 upon 1.4 times the best fit period. These are the empirical formulas. So what the code does, the ASC code, it permits you some relaxation. And that relaxation is 40%, up to 40% depending upon various situation. So the ASC takes care of this, bandwidth, but the Indian code is very strict. It follows only the lower limit and does not give you any benefit whatsoever, which ideally should have been given because this formula essentially is copied from the ASC code. Now, fundamental time period is 0.075 h to the power 0.75 is for RC buildings and 0.085 h to the power 0.75 for moment resistant steel buildings. Okay, and there's another formula given for brace frames and infill wall frames. T is equal to 0.09 h upon root d. This formula is totally outdated. This is based on infill walls. Now, Uniform Building Code of USA was very popular on the west coast of USA due to its seismicity. In the 1970 edition, it introduced the following equation to determine the time period of non-movement resistant frame buildings. Okay, H and D. This formula was adopted in IS 193 in 1985 edition, and it has been retained ever since. Okay, but there is a systematic effort to make the 193 code more stringent with each revision and amendment. The other international codes, such as ASCE 7 and Eurocode 8, do not use this equation at all. This formula has been deleted in these codes for the last more than 20 years. Okay, but in Indian code, they have retained it in spite of different objections, high objections to delete this formula. They have chosen not to delete it. They would like to have a very, very high earthquake force, which is not really, logical. Now, they have explained the values of H and D through figures 585E. Definition of height H. This formula, height H, is also applicable to the formula T is equal to 0.075 H to the power 0.75. So it says height M in building, see figure 5. This excludes the basement stories where basement story walls are connected with the ground floor deck or fitted between the building columns, but include the basement story when they are not so connected. What does it mean? This is the figure 5A, 5B, and 5C. In the figure 5A, you have a ground level is shown there, and the building is going a few meters inside the ground level. Okay, and there are no shear walls, and therefore height H is taken up to the bottom of the building, okay, as shown here, figure E, and D is the depth of the building, which is again shown in figure 5A. Okay, now in figure 5B, you see below the ground level, there are shear walls, which are shown by thick lines. Okay, so because shear walls are there, which is, and so this portion below the ground level forms an independent or a very stiff, portion of the building. Therefore, the height of the building is taken up to the top of the ground level. Okay. Similarly, the depth of the building is taken at D, as shown in figure 5B. The basic difference between figure 5A and 5B is that in the figure 5A, there is no shear wall in the below the ground level, whereas in figure 5B, there are shear walls shown by thick lines. So because of that, height H is different in the two cases. In figure 5C, again, there are shear walls below the ground level, and there is a floor at the ground level itself. Therefore, height H is taken up to the ground level. Okay, similarly, D is also taken as shown in the figure 5C. I hope with this explanation, the meaning of figure 5A, 5B, and 5C is clear. So this was requested by Mr. Ghosh is to specifically discuss this particular issue. Now, another figure is 5D. Now, what is happening in figure 5D? In this figure 5D, you have the lower portion is a plaza. They call it plaza. They have plaza building, and they have a then few stories plaza which meant for parking or shopping center, and then you have a very tall tower. Okay. So what in figure 5D they have done? They have introduced a very retrograde formula for height H. They say take a equivalent height of this building, and they have given the formula in the figure 5D itself. So it reduces the height of the building drastically, and therefore it also reduces the time period of the building drastically. And therefore it increases the lateral force acting on the building significantly, several times more. The concept of weightage height in building with plaza floors. Thereby, it increases the base shear manifold. Needless to say that this change clause is unique to Indian code and without any serious application of their mind. The way it has been introduced in 2016 code, it largely went unnoticed by most designers because this formula was given in the figure, not in the text. Okay, so unless you are specifically making use of it, you wouldn't know that this formula has been modified. It's simply crazy. This is for height H if you are having a building located in hills. There are cutouts and there are different levels of the building. So height H is defined like this for buildings in hills. Now fundamental period clause 7.6.2 in building with RC structural walls, they will given this formula which is based on Eurocode 8 clause part 1 clause 43322 where the total effective area of the walls is given in the first story like this. Now, if you are using the formulas given by this formula h by d, this clause d is equal to 0.79 h by root square root d. You find that the difference with respect to clause 7.6.1 in case I have analyzed 5 different buildings G plus 7, G plus 8, G plus 9, 10, and 11. And you can see that I've given the various values, and with respect to clause 7.6.1, the increase in the base shear due to the formula 0.09 h by root d is 30% to 76%. They are simply crazy and they are simply not willing to listen to delete this formula as has been deleted already in international courts. Now, what to do in such cases where you have a plaza and tower above it? The period of such building should be estimated using either the Rayleigh's equation or frequency analysis. The use of weightage height as specified in the code is a very big disaster. Now, coming to stiffness modifiers. Clause 6431 requires that for structural analysis, the RC beams and columns are to be treated as cracked, and therefore their structural stiffness must be reduced for analysis because you are dealing with limited state of collapse. Designing a building for limited state of collapse due to the earthquake force. At the time of collapse, there would be large-scale cracking in beams and columns. Therefore, their stiffness would reduce because of the cracking. Okay. A lot of designers are confused with the word analysis. They think that the design forces obtained are not applicable to design. This is an incorrect understanding. It simply means that the design forces so obtained by using the stiffness modifiers for their stiffness ought to be used in design. Otherwise, what is the use of such analysis? Okay, that means bending moment, shear force, axial force, etc., obtained by using the reduced stiffness, using the stiffness modifiers. Those forces are to be used for the design of the building. Okay. Please recall that IS 406 also has similar clause 22.3, which gives you 3 options for member stiffness. Okay. What are those 3 options? The first option was use gross moment inertia. Second was use transformed moment inertia. Third was use cracked moment inertia. It was there since 1964 or 1978 at least. Okay. But because we use the gross moment inertia is the easiest option. Therefore, everybody was using gross moment inertia. Okay. But now in 1893, they have made it mandatory to use stiffness modifiers. Therefore, this debate has now arisen. Now, what is the effect of stiffness modifier on the building as such? There are 2 profound effects. One is a reduced lateral stiffness means a higher lateral displacement. It will also affect story drift. Both of them need to be controlled. Okay. Option B is a reduced lateral stiffness means higher natural period. And because the period is higher, therefore the base shear will reduce most of the time. Okay. Under certain cases, the base shear may increase. That's why I have written here, the base shear will change accordingly, depending upon on which part of the response spectra you are located. Okay, so these are the effects. Minimum lateral force. Now, in the 2016 edition, they have introduced minimum base shear for which you have to design a building. Now, after a lot of discussion with a lot of people who are involved with the revision of that code, I was told that the reason is that they think that designers are manipulating the time period or the base shear formula to intentionally arrive at a lower base shear. Okay, so during the meeting of the revision of this code, it was stated that many designers are manipulating the base shear by deliberately choosing wrong values of the parameters and thus arriving at lower design base shear. Now, the basis of writing code can and should never be distrust. This is no way to design or write a code by not trusting the designer. See, if somebody is manipulating like this, he will bear the consequences. Okay? And nobody is crazy enough to let his building collapse. He will never, nobody will do ever intentionally. Never, absolutely never. If you are in your good senses, nobody will ever do such thing that he will make sure that the building will collapse. No, nobody wants the building should collapse or somebody should get hurt. There may be some unintentional mistakes, that's a different issue. Okay, but saying that people are deliberately choosing wrong parameters to reduce the design base shear is simply stupid. So they have specified based on some arbitrary numbers that in clause zone 2, the minimum base shear has to be 0.7% of the seismic weight. Okay. Similarly, 1.1%, 2.4%, these numbers, they arrived are totally arbitrary. Now, I try to back calculate how to get these base shears 0.7% to 2.4%. And I choose uh, uh, zone 2, 3, 4, 5. For I is equal to 1, I is equal to 5, and rho given in table 7, the value SA by G are as follows 0.7, 0.68, 0.667, 0.666. It means for a hard soil, period of structure is given by 1.43, 1.45, 1.5 seconds. It means for a hard soil, it means a structure cannot have a fundamental period more than 1.5 seconds for the purpose of computing the base shear. So for hard soil, they are forcing the fundamental period to be maximum 1.5 seconds, which I think is again absurd. Static and dynamic analysis. There was study dynamic analysis given in 84 code, 2002 code, and then 2016 code. It is interesting to see how the applicability of static and dynamic methods to various buildings has been changed with each revision without any logical evidence. Earlier, codes including 2002 were applicable to framed buildings as follows. Okay, until 2002 means until the introduction of 2016 code. That means till 2016, we were following 2002 code or the previous edition, 84 edition or previous editions. For regular buildings only, zone 2 and 3, height up to less than 90 meters, you could use seismic coefficient method. Can you believe this? Till 2016, June or July, before this new code was introduced, you could use seismic coefficient method in size zone 2 and 3 up to 90 meters high buildings. And suddenly, with the arrival of this new code, this became illegal, unsafe. What is the basis? Nobody knows. Has somebody done some analysis? Is there any evidence of any damage to such buildings designed using the static seismic method in size zone 2 and 3? Not a single case is there. Similarly, size zone 4 and 5, up to 40 meters height, you could use seismic coefficient method. Okay. For all other regular buildings, response vector method. For irregular buildings only, in zone 2 and 3, up to 40 meters, you could use response vector method. I mean, beyond 40 meters, you could use response vector method, and up to 40 meters, you could use seismic coefficient method. In zone 4 and 5, up to 12 meters, you could use seismic coefficient method, and beyond 12 meters, that means about 4 stories, you can go for response spectrum method. So this was there till 2016 code was introduced in 2016, sometimes in I think June or July, August. Now, applicability of static method analysis for seismic loads. Static method gives fairly safe design for smaller frame regular buildings. Such buildings can be easily designed by vast number of regular designers who have only BTech as their qualification, who may not be expert in structural dynamics. Just because commercial softwares are easily available, it does not necessarily mean that these must be deployed for such routine structures. It is based on the first mode of evaluation, a well-tested and appreciated approach for seismic loads. Okay, seismic study method of analysis, seismic loads. Okay, seismic erosion method 1893 2016, clause 7.6 suddenly made the seismic erosion method applicable to regular building less than 15 meters in height in zone 2 only, and response spectrum method applicable for all the buildings. Now, I don't understand, how do they bring in such sudden changes without any basis, without any application in the mind, and they come with these, laughable specifications. Nobody knows what is the basis of this change. There is no evidence whatsoever as far as field observations are concerned. Foundation modeling. 1993 is silent about foundation modeling. However, ASC 7 clause 12.7.1 deals with foundation modeling. For the purpose of determining seismic loads, it is permitted to consider the structure to be fixed at the base. Alternatively, where foundation flexibility is considered, it shall be done in accordance with clause 12.13.3 of chapter 19 as in ASC 7. So, if you want detailed specifications, please refer ASC 7 clause 12.7.1. Okay. Now, in Indian specifications, you have a RC column, you have a plinth beam, you have a foundation beam, that's the physical model. Okay. And on the right hand side, I have shown the computer model. Okay. That's how you can do the modeling, and you can treat the base of the column as pin, because the moment acting, pendulums acting on the columns will be balanced at the foundation beam level. So the foundation beam will carry the moments appearing in the column, and therefore, as far as the base of the column is concerned, it will carry only axial force. Moments will be, restricted at the foundation beam level itself. Column pin as base. The previous figure is typical for frames that do not extend through the floors below grade. This assumption results in the most flexible column-based instead. The high flexibility will lengthen the period of the building, resulting in a lower calculated weight shear but larger calculated drift. Pin distance at the column base will also simplify the design of the footing. Because now you're designing the footing only for the vertical load or the axial load force, not the moments. Now you have another option where you have RC column, plinth beam, and raft or pile cap. So you have a physical model and then you have a computer model. The computer model, the column is treated as fixed at the top of the raft or pile cap. Okay, and because you have a raft or a pile cap, it can take enormous bending moment. The another figure which tells you, what to do in different cases: basement floor diaphragm, base fixity, and basement wall, etc. Moment frame extending through the basement. Okay, this figure was taken from ASC 7 figure. Torsion. Now, if you have unsymmetrical, stiffness distribution, then you can get the torsion in the building about the vertical axis of rotation. Okay, so you have a corner store, a store in the middle, that is the front building, and a corner building where you have only one wall and all three sides you have glazing, steel or your glass glazing. Okay, so because of this asymmetry in the middle case, center of resistance is shown there, center of mass also shown, and because of the distance between the or the eccentricity between center of resistance and center of mass, you have torsion. Okay, and torsion is the highly undesirable phenomenon. Now, torsion analysis, placement of walls is very, very critical. Whether you put the walls around the periphery or around the staircase or central core, or placement of closely spaced columns. This is one option where you have the walls placed at the core and center of the building and only columns all around the periphery and in the middle of the building. This is not recommended. Here you have in thick lines, I have shown the RC shear walls. You have shear wall at the corner and the perimeter also, as well as in the middle. Okay, these are desirable locations for stiffening elements in the building plan. Torsion, there are two design eccentricities specified in the code: EDA 1.5 times E plus 0.05 B and EDB E minus 0.05 B. The first equation is unique to Indian code, because 1.5 factor is there only in the Indian code. It is not there in any other code in the world. Okay, the first equation governs the rigid side of the building and 2 governs the flexible side of the building. I also discussed this torsion in my last week's lecture. Now the forward of the code says that treatment of torsion has been simplified. I don't know how. It is possible to include these equations in E-torsion instead with some difficulty now. Is heaven going to fall if the factor 1.5 is made unity? Are ASC 7 and Eurobond 8 wrong, unsafe, when they ignore the factor 1.5? Surprisingly, this factor 1.5 has been excluded from the time history analysis, but not response factor analysis, as was the case in the 2002 edition. In any case, this eccentricity clause is not applicable while carrying out a time history analysis. Even the 193 2002 permitted the use of factor 1 while carrying out response spectrum analysis. So I don't know why it has been withdrawn. And they are saying they have simplified the analysis. Okay, if you read the code forward, it clearly says the treatment of torsion has been simplified. Okay, I don't know how it has been simplified. I think it has been made difficult and absurd. Now here, I show you the definitions through this diagram. Okay, CR is center of rigidity, that is center of stiffness, and on the other side is center of mass. You have eccentricity along x direction as well as along the y direction. Okay, so if CR is towards CR, this is known as rigid side, and towards the CM, that side is known as the flexible side. Okay, the earthquake is acting, always acts as center of mass. That means the force due to earthquake always acts at the center of mass on each floor. Okay, now the force has to be balanced by reaction. So the building will develop a resistance through the center of rigidity. Okay, the force will act as the center of mass, and the equal and opposite force or the reaction will develop through the center of rigidity. And the distance between center of mass and center of rigidity is E. Therefore, a torsion will develop in plan, which is equal to the force times E, which is shown in this particular figure. Okay, that is the basic definition of the eccentricity. And remember, the total width of the building normal to the direction of the earthquake is B. Here, when you apply the first clause, that is 1.5 times E. So what you do is, this distance between CM and CR, you magnify by a factor 1.5, and you get another center of mass or a CM prime. That is the effective center of mass, CM prime, because of 1.5 E. Okay, so you magnify and increase the distance between CM prime and CR. Okay, that is the intention behind the first clause. In the second clause, E minus 0.05 B. So Cm is shifted towards right. The eccentricity is now reduced. So it is again now Cm prime. So the effective center of mass is Cm prime now, which is shown by EdV, and this is now reduced as compared to E by 0.05b. The term 0.05b, as I discussed in the last term, is known as accidental eccentricity. Okay, various factors, what causes accidental eccentricity, I have already discussed in the last term. Now, what happens here? When torsion is applied, you are applying a force F to center of mass, and there is a reaction F acting at center of rigidity, and the building will twist. Okay, so because of the rigid side, you will see the distance or the displacement, lateral displacement at the rigid side will be very small, as shown by this circle here, and on the flexible side, you will find a very large distance or very large lateral sway. Okay, now elongation requirement of RC column at corners will increase significantly. As I've shown in the other figure, column sway, you can see on the top left corner of this slide, you have column which will undergo this large sway delta. The question is whether your RC column or steel column is able to absorb this huge lateral sway caused by torsion at the flexible side or flexible corner of the building. Okay. Because concrete has limited, elasticity. Similarly, steel also has limited inelasticity. You have connections there, welded connections, riveted connections, bolted connections. Whether they have this much flexibility to absorb this additional elongation in the steel column or RC column. Okay. If not, the concrete will crack, concrete will simply fracture. Okay. Similarly, steel columns will also yield too much or buckle or whatever, and the structure is likely to fail. That is the reason why torsion is to be avoided at any cost. Torsion is fatal. The world over, maximum damage of collapse, both partial and column in RC buildings as well as steel buildings occur due to torsion during an earthquake. The concrete columns and walls unable to meet the elongation requirement at the flexible edges. Similarly, steel is also not able to meet those requirements, and therefore they collapse. I show you the example from Emma Market for Women in Imphal, January 4, 2016. This is before. So this is a small building having central portion is single story, double story height, and all the three sides they have this double story. Outer part is two story, central part is double story height. This is the before the earthquake occurred, and this is after the earthquake has occurred. Short story effect next to the corner column is torsion. You can see the effect of torsion in the corner columns. Otherwise, the building is okay, except the columns are gone. The cover is gone, and core is also gone significantly. Okay. This is also again after another column. You can see here the cover is totally lost, and you lose the confidence in such a building. Now this is a 7-story food building in Agadir in Morocco, 1960. The top 3 stories were in L shape, whereas the lower 4 stories were rectangular. So the building was unsymmetric in the elevation and found more. Okay, and as soon as the earthquake occurs, it will collapse. Torsion is not going to show any mercy whatsoever. Remember, the damage during an earthquake occurs during 5 seconds or 10 seconds maximum. Hardly 5 seconds, not even 10 seconds. Okay. The building has to collapse during a given earthquake. You collapse within any 5 seconds of the strong earthquake in that particular case. It's not going to show any mercy whatsoever. R factor. Shortcoming of ISO 1984, designer had no idea of the factor of safety, reliability of seismic zones or poor. So makes use of elastic response factor without the knowledge of the designer. Okay, so what I'm saying is, even the 1984 code had relied on the inelastic response spectra but without the knowledge of the designer. Okay. It's supposed to be based on work distance method, but internally it was not based on work distance method. It was based on the inelastic behavior of the building. So they thought, let's make it explicit. In 2002 edition, a factor R was introduced so that you understand that what exactly is the R factor and how it has come in. That's how they bring in the concept of MCE and DBE. So the option of the designer is depend heavily on result strength, that is ductility, because we don't know even today what earthquake, what in magnitude earthquake will occur at a given site and when it will occur. Whatever code is given is only estimated forces, but we don't know what is going to be the actual force during an earthquake. So we have to take care of minimum design force in the building and provide ductility to take care of additional force which may come on the building because of the real earthquake. So effect of R factor on strength and displacement, these figures I've already discussed last month in June, so I'm not going to discuss them again. Again, same thing. This is the formula which is given in the 2002 and same in 2016 edition. Z by 2, I by R, SA by G. Okay, this is the formula for the base shear. The basis of R values, last time in that June edition, I also told you how the response reduction factor can be derived, carrying out a actual analysis, actual non-linear analysis. Okay. The values of the various parameters in the equation for horizontal heavy coefficient were developed based on the experience and judgment. The governing criteria was that the base shear determined using 83, 84 code and 2002 edition must be nearly matched in all zones for various time periods. That means the 2002 response spectra was calibrated with respect to the 84 edition for base shear. See, in simplified terms, let me just explain you what does it mean. You have designed a building using 1984 code, let's say in January 2001 or in January 2002. And then you have a 2002 code where the base shear is given by this new formula Z by 2 I by R C by G. And when you calculate the base shear as per the new code, you find this base shear is 50% more. Now, just few months ago, you designed this building using the 84 code because 84 code was applicable until 2002 code was introduced. Now the question arises, if the base shear suddenly is increased by 50% or 20% or even 10%, what do? Building has already been, foundation has already been laid down. Foundation is laid down, columns have already come up. How do you change the design? How do you do the retrofitting? It's not a joke. Okay. Therefore, when you change the formula drastically, you have to make sure that the base shears are nearly equal in the new code and the old code, unless there is a compelling reason to increase the base shear. There has to be irrevocable evidence that the base shear has to be increased because of so many failures which are caused because of the smaller base shear design in the earlier code. Okay. If there is no such evidence, then you have to make sure that the base shear given by the new formula, new code has to be almost same as in the previous edition. Okay. And that's precisely what's done in this case. So we did a lot of parameter study and then came up with the formula for R and I and other factors. So these values of R given in the code, whether it is part 1, part 2, part 3, part 4 of 1893 or even this 16700, they are all based purely on judgment and experience, but calibrated with respect to the 84 edition. Okay. Now, there is another problem which was introduced. The purpose of R factor is to reduce the design base shear to account for ductility and probability of occurrence of earthquake in a given zone. But this objective is negated by using the amplification factor and the partial load factor used in the load combination. Remember 1.5 factor for EL for the earthquake loads. Thus, effective R factor for seismic force reduces from 5 to 5.1.5, 3.33. ASC7 has reduced the amplification factor 1.5 to 1 many years ago. AISC, American Institute of Steel Construction, which introduces steel code for America, they were the first to reduce the factor 1.5 to 1 more than 20 years ago. Okay. Even Indian Road Congress 6 in 2010 edition, in 2010, they reduced the amplification factor from 1.5 to 1, 12 years ago, but not 1893 2016. They love to design the force building for very high earthquake force without any basis, without any logic. The question is, will 1893 part 1 ever correct this anomaly? I don't know. I don't have the answer. Okay, R factor as per NBC 2016, National Building Code, Part 6, Section 6. This is very interesting. Okay, this is table 9, note 1. I'm talking about National Building Code introduced again in 2016, Part 6, Section 6. Because the problem is that our earthquake committee will not listen to anybody. There were so many, requests to modify the R factors or, change this requirement of static analysis, dynamic analysis, and so on, but they are extremely rigid. And one single-minded, no, we have to keep on increasing the force as much as we can. Okay, so what they did in NBC, because NBC was done, this part 6, section 6 refers to steel code, not earthquake code, because earthquake committee is same as in NBC, that which is same as in your 1893 code. So the earthquake committee will never accept a reduced value of R. So what they did, they made a move through the steel code, steel committee of NBC 2016. Table 9 code note 1 says RC and steel structures in seismic zone 3, 4, and 5 shall be designed to be ductile. Hence, this system is not allowed in these seismic zones. It means ordinary frames are explicitly prohibited in seismic zone 3, 4, and 5. However, clause 18.3, table 23 in NBC 2016, part 6, section 6, override this note of IS 1893 2016. So this table 9 I am referring to, and this 1893 2016 code. But there is table 23, clause 18.3, NBC 2016, part 6, section 6. That clause overrides this clause of 1893-16. And that is the table 23 given in NBC 2016. It says non-ductile frames, this is third category, non-ductile frames, the factor is 1.5. Okay. The braced and moment resting frames can be designed as non-ductile frames if their overall height to overall width ratio does not exceed 1, such as in industrial buildings. Such frames need not meet the ductility requirements of other types of frames as specified in 18.4 to 18.11 and 18.13. That means in NVCC and the NVC 2016, clause 18.3, they have introduced clause non-ductile frame 1.5, and they have given a requirement that braced and moment resting frames can be designed as non-ductile frames, which otherwise are not permitted in 1893 2016, with the condition that if their overall height to overall width ratio does not exceed 1, such as in industrial buildings. That means for industrial buildings, you can use a factor of R 1.5 even in seismic zone 5 and complete a design. I think it is a wonderful step taken by this NBC, because otherwise no way this 193 committee would have agreed to such a change. They have done it through the other code, which you can say technically may not be right, but you are not. If everybody is playing their ego, then that is the solution. Infill walls, big infill walls, if the earthquake force acts in a given direction, then there's a diagonal tension developed, diagonal compression is developed. Okay, so and this keeps on changing, with the change in the direction of the earthquake. It may cause damage to the columns, and they have given the formula for masonry, width of brace to represent infill walls. Okay, they have given these formula alpha, etc. for unreinforced masonry walls. Theta is given. Thickness of brace to represent infill is given here. Okay, thickness of the original infill wall provided H/T less than 12. That means your thickness wall should be a short member. Okay, H/T less than 12, L/T less than 12, similar to a RC short column definition where H/T is less than 12. In essence, step 1 is in the analysis for earthquake force that the architect prepare the drawings and pass them to the structural consultant. Step 2 is let the structural consultant run dynamic analysis with different models. Okay, that means you have to assume the member sizes, material, and so on, and carry out dynamic analysis with different models. Step 3, in case of any violation of soft story irregular modes, go back to step 1 for revision. That's what they are saying. Because if there is a violation, if any condition, soft story or irregular modes is being violated in your earthquake code, in your model, then you have to go back to the architect and tell him, please revise your plan, revise your elevation, and let us change the location of the walls or columns or change the sizes and come up with the other alternative and carry out these iterations as long as it is necessary to satisfy the codal requirements. Okay? Because a lot of people come to me to ask, sir, our code, our building does not satisfy the code, what do we do? How to satisfy it? The only solution is go back to the architect. Okay, this is very time consuming, this is very expensive in terms of time as well as money both. And there is no guarantee that second iteration will also give you the correct results. So what does this code does is to force symmetric and regular building in zone 3, 4, and 5. It is killing innovation. Okay. Situations not covered in the code. In any code, the basic intention is to cover the general situations. It is simply not possible to visualize each and every situation in a given structure and provide a specific clause. Therefore, the designers have to be well informed. If a given situation is not covered, they are expected to refer to a specialist literature, reputed international codes, and finally use their experience and judgment, keeping safety uppermost factor in their mind. Okay. So if you want to understand about the dynamic part of it, then you can refer any textbooks or my textbook, which deals with the concepts of dynamic structures. Okay. Thank you very much. Now I will take some questions.
Yes, sir. Perhaps after going through your lecture, we already have a lot more of questions.
Okay.
Firstly, sir, IS 1893 1984, IS 1893 2002, and then 2016. They are all way apart, it seems, in many of the clauses. And 2016 has been developed in such a fashion that there are illogical entrants. So now it is for us, we will be now facing the issues of this new code. So how to solve? That is point number 1. Point number 2, sir, we were taking help of STAD or the other softwares. Now these, as we could understand, that these softwares have started lagging in this part. So how to take care of those? That is my second question. I have a series of questions. And sir, another point, there are different codes. One is 1893 at one side, NBC 2016, the other side. And if we think of steel structures, it is IS 800 chapter 12. So are they overlapping, or is there any mismatch, or is there any issues? So I would request if you can answer these three questions, we will go for the others.
Yes. See, I fully understand that there are a lot of clauses which are contradictory, especially in the 2016 edition. See, I don't think there was such a problem with either the 84 code or even 2002 code. Suddenly, these problems have cropped up only in 2016 edition. And I've already given you the background, how the code was revised and what happened. Okay. Now, the first thing which every designer should do, which almost very few are doing, very few, you can count them on hand, maybe 5, 10, or 20, that if there is a problem that you are not able to satisfy any clause, you should give a detailed background and write to BIS New Delhi. Okay, you have to inform them in writing that I am facing this problem. Please tell me how to solve it. Okay, most of the people are not doing that. So when we talk to the core committee, they say we don't have any representation. If everybody is happy, then why are you complaining? So my advice to the designers is, as soon as you find any difficulty in applying your code clause, please write to the BIS and inform them that this is what is happening. Okay, let them tell you the solution. Either you are making a mistake or they are making a mistake. So let them come up with a solution. Okay. Second thing is you mentioned about the various codes coming in. As I told you, I have already given an example of steel code that you have IS 800 clause chapter 12 and then NBC, where NBC has introduced another clause R is equal to 1.5 for non-ductile structures.
Yes, sir.
Okay, and I also give you the background because people were fed up both with 1893 as well as chapter 12. Okay, so they found a via media, they bypassed both IS 800 committee as well as the this 1893 and made a change in table 23 of NBC. Now, once it is there in NBC, it is bound, it is acceptable to everybody. So you should refer to NBC in your design note that I am following NBC and I will now provide a non-ductile structure in zone 5 for industrial buildings or whatever conditions are there. Okay, that is perfectly acceptable. Nobody can challenge. Nobody can stop you from doing that. Okay, so I think I've answered those
Sir,
three questions.
I had a third question. As we cannot use STAT directly for earthquake, so how to use the STAT for earthquake resistant design? Shall we do it manually? Shall we calculate the horizontal forces manually and then put it in the STAT?
You won't be able to do it manually. The code, your buildings are nowadays so complicated.
Okay.
It can become so complicated, you will not be able to do it. You will be frustrated. You will spend 6 months, 8 months, and in the meantime, the owner will go to some other designer and he will do some hanky panky and finish the design in just 2 days.
Okay, sir. Okay.
Okay. So see the problem. Why you use the word the softwares are lagging. I won't use the word softwares are lagging. The problem with software is, see, they are commercial people. They cannot challenge BIS. They can't complain to the BIS. You and I can complain, but not those software companies.
Okay.
So what they are doing is, whatever they think they can implement, they are implementing it. Whatever they think is not implementable, they can't implement. As simple as that.
Okay.
And they are saying it clearly in their users manual. Okay. So what other people are doing, I spoke to so many designers, they keep coming to me for some advice, and I found that they're all doing manipulations because they have no option. And they're under pressure. Everybody is under pressure to complete the design yesterday. He has to issue the drawings yesterday. Okay. So they are all doing manipulations. And nobody is approaching the BIS. That is the worst part. Because as soon as you approach the BIS, then your project is hung. You can't proceed with your project anymore.
sir.
Okay, that is the reason why they are not approaching them. So the unfortunate part is that, we are in a catch-22 situation. If we approach, we are in trouble. If we don't approach, we are in trouble. And in the meantime, I know there are people who are designing the building even today using 1984 code.
Oh my God.
They are doing it, yes. And that is getting approved even by IITs. Vetting is to be done by IIT.
So
And I know
it's then a very unfortunate situation, because as soon as a new code comes out, the old codes are of no use.
they're supposed to be superseded. They're supposed to be superseded, yes. But who is responsible for this situation? The core committee itself. Right? Why do they come up with such a drastic changes without proper consultation? And
So-
I know other cases when people have given their suggestions, and those suggestions were simply ignored in the core committee.
Oh,
So if your suggestion is there, it's a very useful, very good suggestion, a practical suggestion, but the core committee overrules you. What can you do? And you don't write to them again. Right?
sir, my another point is that if you go through the seismic map of India, the Himalayan belt is in the zone 4 and zone 5 and the northeast, and a small part of Gujarat. Otherwise, the total area is zone 2 and zone 3. So why can't the code be much more lenient in zone 2 and zone 3? That is point number one. Point number two, if we go through IS 800, the load combinations there is dead load plus live load plus wind load stroke earthquake load. So which type of structures can we will avoid for earthquake calculation? So by seeing the structure, or do you have any thumb rule by which you can understand that this structure is prone to wind rather than earthquake, or vice versa? So can you just give some thumb rules here?
Well, I wish I could. See, there are no thumb rules. There are no thumb rules. You mentioned the first part was? First
The
part of the question?
leniency in this, zone 3 and zone 2.
Yeah, I told you. See, I have been complaining on every forum that the present codal committee. See, why there is change in this 2016 edition? Because the chairman of the committee was changed. Earlier, till right from 65 till 2002 edition, the chairman was Dr. A.S. Arya from University of Roorkee.
Right.
Okay. And he was forced to quit under very humiliating conditions by some members of 1893 committee, Codal committee. He was very badly insulted, humiliated, and abused in the BIS committee during the meeting. I was present in that particular meeting. He was forced to resign. Okay. So the new chairman was appointed in 2000 CD 39, under whose official guidance this 2016 code was prepared, but the de facto chairman was somebody else. And again, he was humiliated and he was removed. Since you mentioned about all these problems, let me tell you, right now, there is a very bitter, ugly fight going on for 1893 Part 4 chairman and the other chairman, the main chairman. It's a very ugly fight going on. It is already in through emails for the last couple of months. Okay, so I mean, unfortunately, some dirty situation is going on in the BIS or for various courts committees. Okay, now I already discussed with you here that till 2012, the seismic coefficient method was applicable to 90 meters height. And suddenly in 2016, they changed all that. Now there is no basis, there is no reason. So I don't know what to answer, how to answer this. Okay. So what people do, wherever there is no, IIT vetting or local vetting is there, or there is no vetting at all, they are following the 2002 edition code. So
Okay.
that is much more logical.
Sir, it seems very logical because we are quite conversant with 2002. So we find it quite simpler and quite logical also.
That's what I'm saying. Because at that time, the chairman was himself a very good, a person with deep knowledge. He was himself a designer and he knew the problems. Okay. And at that time, everything was very transparently discussed in the codal committees. So anybody could raise any question and that would be answered. And then there was no ego issue at that time. Okay. Therefore, till 2002 edition, I would say, although I should not say it, but under the circumstances, if you think that 2002 edition you can use, go ahead and use it. Because in any case, that code was used until 2016. And since there are difficulties in 2016 edition, I suggest why not use 2002 edition? Why not?
Sir, another question, perhaps it will be sounding quite humorous, that now the shape of the building for earthquake is to be decided after going through this code so that the calculations can be simplified. Say irregularities, no more regular building. It should have some shear walls, no soft stories. So in that way, back calculation, I mean to say the back calculating to reduce the calculation part of this seismic code, then an architect can only finalize the shape of a building and simplify the work of a structural engineer.
Yeah, but ITER is not going to listen to you. See, what happens now, the ITER will simply change the designer.
Oh.
Right?
Yes, sir.
He will say, you fired this designer, he doesn't understand what is going on. Let's go to Mr. A. He will just finish the job in 2 days. In most of the buildings, it is the architect who governs, who controls everything. Right? He will get it changed immediately. If you
Okay, sir,
ask
I
him-
would. I have been asking questions. If there are questions from others, you may please raise it just now in this forum. Sir, we would put this lecture because it takes a lot of time to digest. It has so much of heavy content.
Yes, yes.
We will put your lectures in our YouTube channel and we have to go through it again, might be twice or thrice to really get into the crux of the matter. So I would request the participants also to check our YouTube channel after 2 or 3 days, and you will get the presentation there. So if somebody else has any question, I would request to raise it.
Yes, sir. My name
Yes,
is
sir.
Praveen.
Yes, please.
Yeah, I'm doing industrial practice. Okay. So my question is that it is necessary dynamic analysis for the industrial building.
I think yes, because if you remember the part 4, it clearly says that you have to find out the time period using modal analysis. You get it? How do you find the time?
Not get it.
How do you get the time period of the building, industry building? T. You can't use those empirical formulas. You can't use those empirical formulas given in the part 1. No, they're not applicable.
No, we are using the first one. That is means part 1. We have followed the part 1, not industrial code.
If you are
Part
designing
4.
an industrial building, then part 1 is not applicable. The codal form, the time period formula, 0.075 or 0.08 or h by d, they're not applicable.
Okay.
And it is clearly mentioned in part 4 that you have to carry out the modal analysis and use that straight away.
Okay, okay, sir.
Sir,
Yes, please.
sir, you discussed about the definition of soft story and weak story. So I think we are going in negative direction. We are moving towards the performance-based design. Where we want the structure to be more undergo more inelastic behavior. But if we use that definition, which is in new IS code, according to that, it will go in opposite direction. Like it will be more conservative.
How? See, the question is when it says that it should be less. How much less?
Yeah, so that is the problem, because in previous it was defined that this much should be there. Now they are saying if it is even 1%, then it will become conservative. They are saying about they are giving the gap of about 30%. Uh, so that gap is reduced. So it is more conservative.
It is ridiculous, not conservative. It is ridiculous. In the question of see, what do you mean by conservative? We have to design a building which is engineering which makes sense.
Yes, sir. It doesn't make sense with conservative also. That's what I want to say.
That's what I'm saying. So the thing is that these definitions should be quantitative, not qualitative. And the quantitative definition was there for the last 20 years, 30 years. Why change to qualitative? What for? See, if everything has to be made so bulky, why do we need a design? And you have used the wrong term when you say performance-based design. That term is absolutely misleading. And so far, there is no Indian code which talks about performance-based design.
Yes, sir. Yes, sir. That is also a problem.
So I don't see nowadays people love to use different definitions. Okay. So that term called performance-based design is not there at all anywhere. And nobody is following the performance-based design. In performance-based design, you're not supposed to have any code. You're only supposed to develop everything yourself. So please understand what is the meaning of performance-based design.
Yes, sir.
Okay. So when you use the term that we are going towards performance-based design, no, it's not true. It is a simple basic requirement that no mechanism should develop, no plastic hinge mechanism should develop in a building, whether it is steel building or it is a RC building. Okay.
So there is a
So,
question in the chat box. Okay, okay.
Sir,
Narayan,
like
if you have,
we follow the limit state method. What does the ASC follow, sir?
Also follow limit set.
They also follow limit state.
Yeah.
But
Everybody is
there,
following.
but there are so many discrepancies, or I will say differences. Like in the steel structures, residual compressive strength. Like sir, in one of your previous lecture, we discussed about the residual compressive strength. You have done experiment on that. So there is no discussion in our IS course about that. Means there is no even a single sentence about that.
No. See, the thing is, as I mentioned in my earlier lecture, that everything cannot be included in the code. Okay. So you have to refer to specialist literature for advanced designs.
No, for simple design also, sir, it is not given. Like for a simple concentric braced frame, they are saying we must consider 33% residual compressive strength. You said, sir, you find 55% residual strength. So that thing we are considering zero. So we are.
No. See, it does not mean we are considering zero. It only means our code is silent. Our code is incomplete.
Yes, sir. Yes, sir.
Okay. See, the problem is that this is the problem. IS 800 code 2007 was based on the Eurocode 3.
Yes, sir. Yes, sir.
Okay. And that code does not talk about earthquake. And 13920 talks about earthquake, and they don't have a corresponding code in steel which talks about the ductile detailing. So the IS 800 committee thought of including a chapter 12 with some minimum requirements which were hurriedly put together. Okay.
Yes.
That's why you have all those discrepancies and all those confusions and other questions.
So can we follow ASC code in India? Like
Why not?
I usually follow that because there are so many differences. I have to follow that ASC code because there are so many
See,
differences.
there's a very simple way to do it. When you take up a project or whosoever is the building authority, you tell them in writing that IS 800 code does not cover these aspects. And they are covered in ASC 7 or AISC code. And therefore, you will like to follow AISC code. And once the the owner, they agree, and the proof checker, if at all is there, they agree, then you can do whatever you want.
Yes.
But that has to be done before the start of the project, or at the time of start of the project. That's the first step that has to be done. So once the project has started, and you raise this issue after 6 months or 2 years, then nobody is going to accept it.
Yes.
So, with mutual understanding, it can be done. Why not? You can say that we'll follow ACI code. Fine, go ahead, follow ACI code. Only thing you have to make sure that there, as far as possible, there should not be any contradiction with respect to IS code.
Yes, they are lacking. Means if we say something, they are lacking. Means if we want to add something like this residual compression, they are lacking. Means they are not wrong. Means I cannot say that, but I don't find them wrong, but they are incomplete.
That's what I'm saying. As long as you satisfy more conditions or more specifications over and above the IS
Yes.
codes, it is acceptable.
Yes. Thank you, sir.
So what I understand is that IS 800 is again undergoing a revision. The committee is working on it. So perhaps within a very short time, a new format of the code will be coming out.
That's so. See, the problem is, as far as the upper part is concerned, somebody else has a monopoly. Okay. And wait a minute. I think this 193 code, they have already taken out a draft for ductile detailing of steel structures.
Okay.
Sir, one more thing, sir. Sir, in ASC code, they discuss about repeated loading, the cyclic loading. They give graphs for how to apply the cyclic load and all. There is no discussion in our code about that also.
Yeah, हमारे यहाँ ना, in Indian code, our problem is our designers, most of them don't know how to apply seismic coefficient method. If they don't know how to apply seismic coefficient method, if they don't know how to apply response factor method, how can you go for dynamic loading or cyclic loading? We are having so much difficulty with IS 800 code, which was issued in 2007. Even today in 2022, most people don't know how to use IS 800 2007 code. I'm sure inside people know it.
Yes, sir. For that, we had conducted various training programs all over the country, but still there are laggings.
That's what I'm saying.
We should understand that.
It's really what I'm saying. That in spite of your best efforts, there are still people in Delhi. I know the number of people in Delhi and Bombay and other cities where they don't know how to design a steel structure using IS 800 2007 code. They're not following limited design. What they do is, at the back of it, they do working stress method using the earlier 84 code.
Yes, sir.
And then they give you some temporary calculations corresponding to 2007, and they say now it is done. So it is again a manipulation.
So even if there were certain documents of the government in the tender specifications also, it was written 1984. So those in most of the cases has been changed, but still there are in many of the state government projects. So there is one question in the chat box.
Okay.
If you can reply to that. Most of the residential buildings these days have stills. How to avoid soft story? This is the question.
Yeah, I give you the solution there. You have to provide shear walls or braces in the plane of the frame, so that the movement of the car movement is not hampered. That's not disturbed. So you have to arrange them in such a manner that cars can come and go. But you have to provide walls at certain locations, not everywhere. Or you can provide shear walls, or you can provide steel braces.
So I hope if anybody still have any question, we can chip in.
Sir, for the previous question, I have seen one paper where they have used lintel band in RCC building.
That
So
is
like
ridiculous.
for
That is
previous,
ridiculous. There's not supposed to be any lintel band in RC buildings. No, that's the wrong interpretation again.
the band was made up of steel, not RC. The
Doesn't
structure
matter.
was
Doesn't matter. It's not supposed to be there. It's not supposed to be there.
yes.
Okay, sir, I think there is no more question. So this part of the lecture was quite interesting and quite confusing also to some extent because of the deviations from 1984 to 2002 to 2016.
Yes.
So I would request participants to go through the lecture, which will be there in the YouTube. And if you have any questions, you can directly throw it to us. We can send it to Dr. Jain, or you can directly also interact with him. So with this, I think if there is no more questions, we end today's lecture. And we thank Dr. A.K. Jain to discuss this issue, which we never thought will be so much complicated, but which we could understand that what this code has been doing to us for designing.
Yes.
So with this, thanks a lot, sir.
Thank you very much. I enjoy talking to you, talking to the participants. I hope they found something useful in it.
I hope so, because this has given us food for thought also.
Yes, yes, yes.
Yes, sir. With this, we end, and thank you, participants, and we look forward for your participation in our next lecture programs. Please follow us in our website. Thank you all. Good night.